over to you for this time. Thank you.
Thank you, sir, for the kind introduction. Can you hear me? And
Yes,
is my
ma'am.
slide visible?
Yes, yes.
Okay. Sir, I would just like to take 1 minute break. Some important call is coming. So
Sure,
just
sure.
give me
No
1
problem.
minute.
Yeah, no problem.
Mm.
Participants, hopefully you are taking the exam, the quiz exam, the quiz, both the quiz are open. I think today we will close the quiz 2. So for participants who are still taking quiz 2, please ensure that you will complete quiz 2 today. Quiz 3 will be closed tomorrow. So with that, we will generate the result. So there, so that's what I can say as of now. So hopefully all of you will be able to take those exams. Yeah, sure. Chat ready करो. Chat.
Pillai sir, could you just pick your call? I just want to have a word with you.
Yes, yes.
Okay.
Yeah, ma'am. You
So
can go ahead.
very good afternoon. Um, so, you know, I really want to say that I'll be talking more of computing and communication, but it may happen that some slides, as I was seeing the list of, you know, the attendees, it may happen that some of you have already attended. So my apologies. Maybe there may not be, you know, some new content. You know, R&D in this technology doesn't happen that fast. So if you have heard me a month back, then most likely you are going to hear the same things. But given to understand that um, many of the participants are coming for the first time, so I think I'll have something to share and some good results to discuss with you. So I come from a background where I've spent few years in academia and then few years in industry, and now it's been 4 years in a government R&D organization. So here, you know, earlier I had worked on bringing quantum technology working prototypes from theory to on-table experiments, and in a manner such that those working prototypes could lead to a product of TRL level, say six, six or between 6 and 7, and they have been tried, tested, adopted for further R&D in industries. And a lot of work is now you know, being done in the area of quantum communication, because it is at a higher TRL level. And now I'll be you know, I will be moving towards developing prototypes on quantum computing. So with that, we'll start with the basic difference between a bit and a qubit, because that is where all the magic lies. A bit is a binary unit of information, 0 or 1, but a qubit is a quantum analog of a bit, and it it is both 0, 0 and 1. So it is represented here with a block sphere, and you can see ket0, ket1 are the quantum states that represents logic 0, logic 1. These are computational basis states. And the equation you are seeing here, ket xi shows alpha ket 0 plus beta ket 1. Alpha and beta are complex numbers in a manner that mod alpha square plus mod beta square is equals to 1. What does that mean? We'll come to that later. Now, just like every bit is represented by a voltage level, so these are physical quantities, right? So it has a physical representation. Similarly, a qubit, now a photon is a flying qubit. Qubit will also have a physical representation. And in this presentation, we will be talking mostly in terms of polarization degree of freedom of a photon. So a horizontal and a vertical in computational basis would be represented by ket 0 and ket 1, right? And when you have a qubit, when you have quantum algorithms, then you need quantum circuits. And for that, you need quantum gates. A classical gate, for example, say a NOT gate, is represented by a transistor on a breadboard, as you can see here. Similarly, a quantum NOT gate can be represented by an optical device that can take a state from a horizontal to a vertical. If I'm representing it as ket 0 as horizontal and ket 1 as vertical. Okay, so ket xi is my input state and ket xi output is my output state. And this optical device can be half-wave plate that can rotate the polarization and take it from 0 and to 1. And there is a stable output, you know. I'm not getting into the 5 conditions of, you know, of a quantum computer, where stability is one of the one of the criteria. It should not come back again to get 0 state, or it should not be in a superposition. of 0 and 1, and sometimes you're able to see a not one state. So it has to be stable, and it should always lead to a 90-degree say shift in polarization. And so a zero gate can be a horizontal gate state, can be a vertical state after it passes through this half wave plane. So this is how we can do or realize um, gates in lab, or in if you're looking at establishing an education lab in your institute or in university or any center of excellence on quantum education. So optics, it is can be affordable, and experimentation on quantum optics. If you are able to do experimentation on quantum optics, you will be able to explore several verticals of quantum technologies, per se, then quantum computing, then and quantum communication and quantum metrology. Okay, so it's a very interesting branch of you know where different use cases can be explored. Now, when you talk about superposition, then classically superposition do exist, but what we mean in quantum superposition is a state being in both zero in multiple logic states. See, if it is not binary logic, if it is qt logic, then it can be the state existing in more than two states. So let me say multiple states simultaneously. um, for example, as you have okay, okay, so for example, if you take a beam splitter, a beam splitter is an optical device which sends half of the input beam in the transmitted path and half of the input beam in the reflected path. But when you are given a photon, you know it cannot divide the energy. So how it interacts with the photon is very different than how it interacts with a cluster of photons. So when one photon strikes the beam splitter, the output is the photon exists in both the path, transmitted and reflected path, at the same time. Now, it is quite counterintuitive, but if you look at the maths, if you do the maths, you take the input state, say get xi, get 0. You represent this as a column vector. You represent the beam splitter as a 2 cross 2 matrix. Then when you apply the state, you will see that it exists in both the column vector at the output. It gives 1 1 in both states. So it shows that mathematically the state is existing in both transmitted and reflected path. Further, uh, you may want to build an interferometer, a Mach center interferometer, and then pass a single photon through the interferometer in a manner that the photon, after the first beam splitter, if it exists between both the paths, it will meet itself at the second beam splitter. It will interfere with itself, and you will see the interference effect at the output. Now, such experiments can be done in lab. Such experiments can be mathematically explained to the students to gain their confidence, and to show that how the maths actually tells you what you will be seeing. And if you're not seeing the superposition, if you're not seeing the right answer, then that means something wrong with the setup, some alignment, or something has gone wrong with the experimental setup. Okay, so here a professor was explaining. I'm so sorry. The professor was explaining superposition, and then he asked the students to give an example of quantum superposition. Then the boy said mermaid, but then the professor said, well, nobody has seen a mermaid. And then the boy says, that's exactly because the moment you observe, I would rather put my mobile in. in do not disturb mode. So that is, the professor says that the boy says that it's simple because the moment you're trying to observe the mermaid, it either collapses to a fish or to a girl. But then the professor also says that if there is a basis where the mermaid itself is a state, then if you do measurement in that basis, you will be able to see a mermaid, right? Now, now this statement, actually, this figure is from my professor's book. It's drawn by Kathakali, and that is why my professor, uh, you know, told me that this is also a possibility. And I'm sure once you listen to this lecture at the end of certain principles which I have explained, you will be able to take this down with your students as well. So just in brief, the mermaid and the fish and the girl are ket 0 and ket 1, and the mermaid is a diagonal state. So if you do a measurement in the diagonal state, not in the computational basis state, then you will be able to see a mermaid. So now we would like to see how this whole thing, the superposition can be can be explained in lab to students. And for that, and there have been quite a few research papers where such experiments are explained to high school students, to college students, undergrads, and this is one of them. But first, we have to generate the single photon state, or the photon, correlated photon. And for that, we use spontaneous parametric down conversion, because we the correlated daughter photons which comes out from a single photon, obeying the energy momentum condition, and the condition is satisfied only at a when the photon interacts, or when the light interacts with a particular type of a crystal at a particular in a particular manner, then the phase matching condition is achieved, and we can see the single photon coming out from the beam. And this is the picture which we have shown here. So we use some advanced detectors to capture for a visual confirmation of the phase matching condition, right? And after we have done that, then we capture this. So this is the energy momentum criteria, and then this is the basic setup, which comprises of laser source. Now this cannot be just any laser; it must have certain specs of certain nature, which will qualify itself such that it falls on the crystal and you're able to generate the single photon states. So these are HWP are the half wave plates, and these are band pass filters. M stands for mirrors, L stands for lens, I for iris. So when the light falls on through the wave plate, through the polarization beam splitter, in order to pass a certain wavelength, a certain polarization of light on the crystal, then at some condition, this light is generated. If laser is emitting some millions of photons, then 1 in million or billion is going to generate single photons. The rate of single photons is very less. The probability that you will have two correlated photons only generated is also very less. And if you are able to generate high output single photon states, then much of the problem of quantum cryptography will be solved. But the scientists and engineers believe that they are exploring different ways of generating single photons. But this schematic is something which can be done in your optics lab, physics lab. Yes, but there are some difficulties. For example, the detection system here, it consists of silicon detectors having efficiency of 70 to 75% at a particular wavelength. And if exposed to the light, even your torch, it may burn out. So, and even the crystals here, hygroscopic, maintain the temperature. The you you know it can can hamper the performance of the system. So you need good class one, what's it, 10,000 cc is also okay. Some good lab to conduct these kind of an experiments. And again, such experiments will not also be accessible to many students in a batch. So there lies the necessity of to bring out such experiments being accessible to multiple students. Now, when I was talking about the quantum gates here, this is a single qubit gate. That means one input and one output. Now we will be able to demonstrate such single qubit gates, poly X, poly Z, Hadamard gate, some phase gates. I would not say all, but if you would want to generate an arbitrary quantum gate, then of course it is possible through this mechanism, but that is again some deep research involved. But for basic lab, you should be able to generate some not some gates and demonstrate that to the students. This will help them to not only appreciate but also to for explore the engineering, because apart from the quantum light which is interacting with the classical gadget, rest of all is very much used for different applications in the classical world. The detectors, the mirrors, these are all classical mirrors, but they do have, I mean, they have a special coating. They cater to a particular wavelength. So these are specialized, highly specialized. Um, you will need mounts, um, mechanical mounts, kinematic mounts, the mechatronics, the optoelectronics. So all that, those are very much classical, right? The quantum part lies in the physics, in the when the light is interacting with the nonlinear crystal. Except that, except that path, everything else would be um, classical in nature. Now, this is a superconducting based quantum computer, and the one I was talking about is a single photon um, quantum computer, which cannot be scaled up. Okay, but this is just for quantum education purpose. And the one you are seeing here comprises of artificial atoms, and they need a special temperature to operate. And you can see the wiring here. This is called the wiring problem because you need to control a qubit which is inside a cryogenic at a temperature which is less than the outer space to be controlled by these control units, right? And the quantum circuits sits on this compute hardware, which actually gives commands to the control pulses, and accordingly the control pulses are formed and they manipulate the qubit, and then finally they are also sent back to be read out. So again, all of these calls for a lot of R&D in engineering, like streams like electronics, mechanical, thermodynamics, electrical, the different disciplines altogether. So there's a lot of engineering R&D involved in the development of any of the quantum technology device, be it a quantum communication, quantum optics based device, or a quantum superconducting based. So now to demystify the quantum computing, we need to build an accessible module for students. And this was motivated by a student from a college in Pune approaching me for a internship, and she was building a simulator, quantum simulator, like Qiskit. So then we propose that we can build the backend and the middleware and the software stack that will enable actual quantum operations on her simulator. So we did work on simulator as well. She was leading a team of 2 to 3 students. So you can think of her being, one of the team leads or group leads. So this is the simulator. Now, such simulators can also be built by any students. And then you have these gates quantum gates: NOT gate, identity gate, Hadamard gate, um, phase gate, Y gate. Okay, so you can drag and drop them. I should be able to show you the demo as well. You can drag drop those gates. Now, what happens at the back end? Now, just like unlike the classical circuit, once if you do a measurement, a NOT gate will remain a NOT gate. But because in quantum you have this superposition and you have probabilistic nature, you will have multiple measurements, multiple outcomes. So you will have to take the average of the outcomes. So it is an excellent way to enable student to understand how a quantum system or how a quantum state works. Even if you look at the basic postulates of quantum mechanics, quantum measurement, quantum state, definition of a quantum state, um, those things can be better understood once you're actually working on a system. Now, earlier there was a company who had come up with 2-qubit NMR based quantum computer, and this one which we have built is actually a single qubit photonic based optics based quantum computer. And this can be used once you have the quantum single photon source ready. You can also be using it for different R&D purposes. As I told you, quantum optics is the basis for different technologies: sensing, metrology, communication, cryptography. Um, so this is a very good kit for using it to generate single photon states for your further R&D. You can also use it for developing your own quantum device, for example, single photon detectors, and then benchmarking it or substituting it. We can help you with that. You can make your fibers. You can there are things which maybe I am not able to think of, maybe laser. So very advanced level of R&D can be done, especially for the faculties. um, so yes, so here when I run this demo, you will see that gates are being dragged and dropped here, and then you will see the counts: logic 0 and logic 1. If my base state is a horizontal and I apply an identity, it stays horizontal, but it will never be 100%. You will see the simulation results, it will show 100% result. But if you see the practical, you will see large number of counts in logic 0 and lesser number of counts in logic 1. So you also need to understand, you see, one very important, I was talking to Pillai sir also, it's a very important point to understand the loopholes when you are working in, or to understand the loopholes, advance the engineering, right? So when I will be running it here, you will be seeing some noise: maximum counts in logic 0 and minimum counts in logic 1. That is a noise. So you can play around, you can identify from where are the different sources of noise, how can I reduce them. If you would want to work on quantum computer, then you can work on algorithms on noise mitigation. You understand the system, and you can work on introducing noise also as per the system. So lot of R&D based on quantum computing can be formulated using this education module. Now, this is, well, I mean, I would also say this is something you can build on your own in your lab. There are research papers. I can help you by sharing those research papers. But since I come from a background where I started off with an electronics, master's in electronics, then I did my PhD in theoretical physics, and then I worked with the experimentalist, and I developed a working prototype. So this is not something which can be done with one or two manpower. You need interdisciplinary manpower. You need sustained manpower, and quite a professional one. And since in an R&D organization we have people from different departments who can come and pitch in, and we had lots of MTechs in quantum technologies, and that is the reason we could build this up. Though we were building it for a different experiment, but this was a spin out because of that that young mind which had come and started asking us to guide her in her internship. Unless that would have happened, this would have never come out as a professional, as a working prototype. So let me start this. Now, something very good is we also you also don't need a clean room to run this experiment. The way we are going to facilitate you, you can run it on, because to build this, it has absolute as much as possible, not absolute, because you'll be already getting a noise of about 100 or 150 counts as noise, visible light. So it can be light, right? So to decrease noise in the system, you need to create that ambience, work. So here, as identity gate, you can see the Python code and you can see simulation results. It's showing 100%. Then it says measurements has been completed, and then you will see maximum count 6,000 in the logic 0. Now we are dragging and dropping, I think, NOT gate X, which is the NOT gate. So logic 0 will become logic 1. In simulation, you will see maximum counts of logic 1. And in real-time result below, you will see logic 1 with some 5,779 and logic. Okay. Then you have Hadamard, which is the super percent in you have the super percent. Now you're measuring the. So this is how this works, and our quantum hardware was in the lab, and the instructions we were giving was from the first floor in our building. So it was remotely done, and the the proof that it is a single photon source. So there is some parameters which we measure, second order correlation function, and if it is below a value, that means you are in quantum regime. Then we go to quantum entanglement. So I would say, for any education body, any academic body, only two things are very important. That is the generation, of course, of the photons, and thereafter the superposition and entanglement. So superposition, demonstrating an application via superposition, demonstrating quantum entanglement, demonstrating one application with quantum entanglement. And along with it, of course, you are generating those states, otherwise you cannot show them. And then you have to do measurement. The essence of quantum technology or any quantum advantage lies in the measurement. Okay. So these things are a must for anybody who would want to explore their future as an entrepreneur, or as or for doing deep research, who, or someone who is trying to come out with good ideas in quantum algorithms. Anybody, but these are the aspects: the superposition, the generation of quantum entanglement, demonstration of quantum entanglement. So this anyway involves measurement. So these two are the very important areas which the students should be exposed to. So, story of a little bit upon the story of entanglement. Of course, it started with in 1935 with Einstein talking about the photon as the energy, and then he is asking the question whether can quantum mechanical description of physical reality be considered complete. And we have heard about it, right? Because he was not comfortable with the idea of a state being non-local, okay, and non-realism. So he was not comfortable with these stuff. Now, before that, let me tell you about this particular state, which is the entangled state. Means a particle or two particles, 1 and 2. And Ketsa here is your entangled state or the quantum state. It's a two particle state, okay? So the entangled state, a two-particle state, is represented by ket HH plus ket VV, means particle 1 and particle 2 are both are horizontal state, particle 1 and particle 2 both are vertically polarized state. Okay, and the denominator square root of 2 is nothing but my alpha and beta, the one which I mentioned in the first slide of this presentation. Okay, so alpha and beta are 1 by square root of 2, and my ket, the two states along with alpha and beta, they are ket HH and ket VV, and this is particle 1 and the second is particle 2. What this means is, if I am measuring the state, entanglement is a special superposition state. So if I'm measuring the state, then I'm able to observe either both the state being horizontally polarized or both the state being vertically polarized. Okay. Now, if I do measurement at some point, which and I get HH, there, then I do not know the other state would be HH or VV. Okay, so mathematically I can show that there is no relation on the outcome of the first event on the second event, or vice versa, or on the prior event to that event. So they are identical and they are independent of each other. The measurements are independent of each other. So now this particular phenomena or this particular state can lead to different applications. Now HHVV are the two particles are correlated. It will be either HH or it will be VV. Okay, so this is one of the Bell state, and I mean, these two states cannot be represented as a separable state. It is not equal to xi1 plus xi2, ket xi1 plus ket xi2. Okay, and also, if I take my first particle if I keep it here with me in Pune, and I send the second particle in some other galaxy, then the moment I'm measuring my particle 1 at Pune, and if it comes out, if it comes out as a horizontal state, then in that moment itself, the other particle, which is in the other galaxy, will collapse to H. Now, what made everybody uncomfortable was, how does the second particle, which is sitting in some other galaxy, know that I have got H? Okay, so that is called, that is non-local, non-locality. Hmm? Similarly, Similarly, if I get V, the other state in the galaxy would be a vertically polarized state. Okay, so and so then there was lot of brainstorming sessions amongst the researchers there, and they came up with a inequality, saying that, well, if there is a classical phenomena, then it has to obey. If there is some classical phenomena, if it is classically involved, then it has to obey that inequality, and we call that Bell inequality. And any classical phenomena, if it is involved, then it will be less than 2. But when the entangled photons were generated through an experiment, and Bell inequality was tested, then the entangled state violated that inequality. And it is for the same experiment that the Zeilinger, Clauser, and I expect, having worked on that inequality and having done and an application of teleportation based on entangled state. Because if you have done quantum teleportation, you know that it is only possible if Alice and Bob shares an entangled state. Then Alice has a particle which she does not know the state about. It's an arbitrary quantum state, and if she tries to know the state, it will collapse. So she has to send the state without knowing what it is to the other side, where Bob is there holding the second particle of the entangled state. So she does some measurement, and then the state appears with Bob. Okay, So that is quantum teleportation. So a Nobel Prize for quantum mechanics was dedicated to to this effort. So so this is a question. These are some of the exercises which you can give to students on verifying the entanglement, whether an entangled state can be written as a separable state or not. Okay, so you have here a two particle state, and you can open this up to write in this manner, and this is an arbitrary two qubit state. Okay, and then you have these four possibilities, and then you can ask the students whether if you can write the entire state as a separable state, which the answer is no. And well, I have already done this for you. So motivated by the Zeilinger aspect and Clauser, we also demonstrated the Bell inequality in lab. So for that, we first had to generate an entangled state, which is the first part. After having, trying to meet the conditions, as I told you, the phase matching condition with the right optics and the right equipments, we got a visual confirmation, which I will show you. The demo I'll show you in the next slide. So after that, then we capture. It's very difficult to capture. It almost is impossible to think. You capture two photons at the intersection points of two rings, and then you send it to the two receivers. Say Charlie generates the entangled photons and gives it to Alice and Bob. Okay, and then Alice and Bob will perform certain experiments. Some I would not say experiments because you don't have a quantum memory, so you need to measure them instantly, as in when you're doing the experiment, um, and then you obtain the S parameter, and then you obtain the S parameter. So here, which we have of course got more than 2, and it should be less than or equal to 2 root 2, which is 2.8, and then we got very good results actually. So this is the ring. Intersection of two rings is where we'll be getting our entangled photons. Okay, so each ring corresponds to one polarization, and the intersection there is an ambiguity. So and we need to capture just the diametrically opposite photon, okay, to observe the correlation. So upon capturing them, then we did the visibility. So we got 98% visibility in the HV basis and 86% in the diagonal basis. And this is also a very good results which we have obtained. And then we got the tomography results where we got 85.39% fidelity. So these are the characterization results which we did. So all of this is done by capturing the photon from the two ends. So here the you can see the blue line, the violet line here, which is this pump laser direction, and you can see the yellow lines here. It's where the photons is coming out from 5-degree angle from the center. Okay, and we put a lens here so that after the lens I can get they can come in a fashion that can be captured. Otherwise, it will continue to expand, and it will be difficult to capture them, right? So a lot of learnings and a lot of corrections had to be done in consultation with scientific domain experts, right? And this could happen. So now let me take you to the camera. I'm trying to capture the out laser and the optics here, and finally it goes to this EMCCD camera, 8 mm by 8 mm window, I think. Yeah. So this is in light. The experiment is still not on. So my detectors are doing it in light. If you have to capture, we'll be switching off this light and you can see the result here. As I told you that the quantum light is very fragile and it's in picowatts, and you can see the intersection here. And then we will be moving the camera, I think, to capture the intersection point at the other end. Yeah. So this is the second intersection point, and now we will be will see that. So here changing the matching condition, and you are seeing that these rings will disappear. The rings are going to disappear. And again, he will bring back the phase matching condition and you will see that the rings will appear. Okay. Yeah. So this is the setup through which we had shown that experiment. And now you see, once you expose this to the students, so before saying that, you have seen that the quantum light was always existing. It's just that we changed or we changed some parameters to enable that physics phenomena to occur, and respecting the energy momentum conditions, and then the quantum light evolved. Okay, but it was always there, right? So this kind of a demonstration, when shown to these students also, it builds their confidence. And since you are actually seeing the system live, you can also think about different ways to improvise the setup, to build different applications out of this setup, whether it be in communication or QRNG or QKD or quantum computing, coming up with of different kind of gates, particularly phase gates or something, you know coming out with some specialized mounts that can solve this problem, because this calls for very precise movement, right? So as I told you, it's multidisciplinary, and such exposure to such instrumentation will help bring more awareness and also build confidence. So I will recommend such experiments in colleges, and maybe in high schools and all. They don't need to fiddle with it, but for MTech, I think this will be critical. For BTech, having worked with with many BTech students, I think it really creates interest in them, and they can align their careers also. They can take a better decision on how to, in which direction to move. And now, with a lot of stress on startups, entrepreneur journeys, this will be helpful. So I've already shown you the results, um, but here I had mentioned only one of the entangled states. There are four states known as four belt states. Okay, and basically HHVB and HVH with plus minus in between. So if you write belt states, you will see, and it is possible to generate all four of them. Um, using BBO nonlinear crystal is one such method. Now that was important for us, because if I'm moving to for any particular application, I may have to use some specialized uh, crystals, some special techniques I need to apply to meet the requirements of the user. But working with BBO is absolutely necessary. It is affordable, and it is quite reasonably, you can come up with the outcome sooner. So this is a very good way to start your journey in the quantum optics area, where you are seeing where you are also working on quantum photon generation, optics generation. You're dealing with different kind of measurements. So in future, when you are looking into quantum communication, and you're trying to understand how a quantum adversary works. Particularly, quantum adversary is one who will be equipped with all knowledge of quantum physics, and he can think of any gadget, any tool which is allowed by quantum physics. So he's not a quantum attacker, a classical attacker, but he's a quantum attacker. He will have quantum memory. He will do generalized measurements on the system. He will have a quantum computer. So, if you're talking even from an attacker perspective or eavesdropping perspective, knowledge about how the physics, and also about the different engineering devices which is which enables such a development is becomes very critical. And even if you would want to repair such devices, I think that this can also be taken up in the national ecosystem as well. And the engineering students can play a very important role, particularly the BTech in electronics, mechanical, on how to work on the particularly these instruments. So now moving forward, now this is the Bell test. Now, Clauser had actually um, he tried making the Bell test experimentable. Okay, so this was the inequality which he had given, and the numbers you are seeing are all polarization degrees. Okay, and this is again very critical, because when I'll be talking about a quantum communication protocol, Eckert 91 and BBM 92, or I'm talking about the preambles of quantum cryptography, Bell test, or such a test of assures you that you are actually working on a quantum device or a quantum state. Now, this also leads to protocols such as measurement device independent protocols, or semi device independent cryptographic protocols, or quantum key sharing, quantum key management, key agreement. So many things can come out if you have a better understanding about the entanglement and superposition. So this is one such example. Now, since we had generated, we could we could quickly come out with a QRNG, and right now the scanning is not activated, but we stored a lot of random numbers generated from the entangled state, and then we had carried on uh, the testing of numbers. Okay, now again, since it's coming from an state and it has say 5,000, very less numbers, and the test suits are usually in megabits, or a large number of data is required to test the randomness. So a better test would be the ENT test profile, which actually measures the randomness for a lesser number of bits, right? And otherwise, you keep on generating the random numbers from an entangled state for a long time until you have some about 10 MB, and then you test the randomness. So that is also very much doable. This is how the test bed looks like. So this is the state. Yeah, I mean, I had explained to you already, so I'll move ahead. We did our benchmarking with the results which we have got, and you will also see some network test beds. So globally, people are working on these prototypes. Now, what they usually do is, if they can buy the prototypes from somewhere, so that they can they can perform the add-on experimentation, add-on research on it. Maybe they're looking at prototyping a network, a quantum network. Then they can have different setups involved. So such network such a setup is called a network test bed. And the Tuscan test bed and the Boston test bed, they do have quantum entanglement as one of their primitives. Now, we'll come to quantum cryptography. Now, cryptography is as old as civilization. It started off with Skytail. Then you had the superposition, transposition, and substitution based ciphers. Then you had the electromechanical based ciphers. Okay. Now, the cryptographic devices or cyber devices, they always have changed based on the technology development. Okay. So you can see here the bomb, which was used to decipher the Enigma. So, and since now we are moving towards a quantum technology era where you have the quantum cryptography redefined, in present, in modern cryptography, uh, if you look at first, let me come at let me discuss this slide. So here you can see the cryptographic architecture. You have a quantum encryption algorithm. You have a plain text going in to this algorithm, and you have a key which is already available at the two devices, at the two ends, with Alice and Bob. Alice and Bob are the famous cryptographic couple. I do not see a reason why the name has been chosen so far, but they are usually most commonly used. Now, even though the encryption and decryption algorithms are known well in advance to the quantum adversaries, um, the, the entire uh, the responsibility of security comes it comes to the keys. So if the keys are secret, then your entire cryptography is secret. So key the quality of key, or how we are generating the key. Now the key here refers to a binary bit string. Okay, perfectly correlated binary bit string at Alice and Bob. A physics process is able to generate a binary bit string at Alice and Bob in a secure fashion that may solve the problem of somebody carrying the key from one place to the other. Okay, now this statement is important because in classical cryptography or in PKI, a pragmatic approach is followed where you generate keys which should be passing the prescribed randomness test suits. If they pass that, now there are certain algorithms to generate random numbers which, you know, they do pass, but they are actually not random if you are testing them with with a slightly different logic, or if you are evaluating their design. They are made to pass the standard test suits. Now, I would not like to enter into a debate, but such had been my given understanding from the experts. So, when the key is compromised, if the key is not compromised, the encryption decryption algorithm is known, your cryptography is good. But when your key is compromised, your algorithm is already known, so everything is compromised. So, the problem lies in the key distribution. So the problem lies in the key distribution. How do Alice and Bob share a secure key in the first place? So there is no means. I mean, if somebody is at least, even if they can at least look into the keys, right? If somebody is looking into the keys, you will not be able to. It doesn't lose data. It doesn't leave any footprint, right? So there is no solution on how you can enable a complete security in by key distributing the keys. One-time pad is an encryption algorithm. It is information theoretic secure, which means that if given um, you know huge unlimited space and time or unlimited resources, you'll be able to decipher them. So one-time pad is information theoretic secure, means this is the only encryption algorithm which is forward secure, or you will not be able to crack it even if you have been given unlimited resources, provided it is the keys which you are using for this algorithm are truly random, they are never reused, and they are as long as the message. Now, these three conditions also pose a limitation of using one-time pad for pragmatically in different applications. So the requirement of generating dynamic, um, on demand, and high entropy keys at two ends, Alice and Bob, stays. Now, this is addressed by quantum cryptography. The ideal rules of quantum of security says that the security should be good as the keys. I have already mentioned this. Should not be copied. If somebody is looking at it, it should be detectable. Or key tampering should be detectable, and it should be random enough. So, in classical security, as I had told you, it relies on computational security, means with some limited resources, you will not be able to break it. With some limited resources, your keys are protected for, say, some billion of years. With maybe some technology advancement, it may be some hundreds of years. Okay, so it is dependent on that. Information theoretic security is the most robust way of approaching the security of a cryptographic architecture. The mathematical hardness, then it relies on PRNG. So the mathematical hardness, for example, the RSA cryptography, it relies on one-way factoring. But if you have a quantum particular problem statement can be broken in few seconds if you have a cracking quantum machine, which is at present the highest priority in several countries to build a logical quantum computer of, say, few hundreds. That will be sufficient. Now, quantum security would mean that now it comes with some rules. Say cloning theorem, non-locality. If you have Since it's a quantum system or a quantum entity, if you are observing the state, then you are perturbing the state. Okay, and that leaves a footprint most of the times. Now, I'm using these words. Most of the time it will leave a footprint, not always, and I would like you to think about why I have said this. Now, why are we so sure about the security of quantum key distribution, and how is a quantum key distribution protocol developed? So let us look into these two questions. Now, before I begin, I hope I'm very much in the network and everybody can hear me.
Yes, ma'am. Yes. Please go ahead.
Okay. Okay.
You are audible, ma'am. Yeah, no problem.
Okay, sir. Thank you. Thank you. Yeah.
If you are taking a break, ma'am, there is a few questions you can take up in the chat maybe. Well, once you change from quantum cryptography to the next topic, you can.
Yeah, I think before, yeah, I think I'll take some questions now because there are lots of cryptography, and then I'll talk about some protocols.
Sure, sure, sure.
Yes. Yes. So one question I can see is, are PQC algorithms developed or under development? Well, PQC, so if you follow the NIST, standards, they have already published few candidates. Almost, these candidates are finalized. Maybe they'll be declaring the final names, which should not be different than the one they have proposed in final round. So it is already announced, and there is a national, global mandate, particularly by Europe and US. to transition to quantum safe cryptography. Now, a quantum safe cryptography, though the mandates are for PQC, globally they are also working, equally hard in the area of quantum key distribution. So QKD, QRNG, and PQC are going to coexist. How are they different from the existing encryption algorithms in practice? Well, if you are exploring that, it may be a little heavy on in the computation because of the size of the keys and because of the processing of these post-quantum algorithms on the compute hardware. I mean, so you may have to use maybe good accelerators, maybe GPUs for if you're looking at it from a data center point of view, because um, for supercomputing applications, it will also have to change to a quantum safe background, right? And such applications, when carried out in huge scale, they have to be complemented with GPUs. We did a few testings with PQC algorithms, and they seem to perform better than when we used it in our workstation compared to 48 core HPC and then to a GPU system. So it is going to be computationally, I think it's going to be challenging, but there will be an adoption, and there will be a change. So about hundreds of international MNC companies, they are transitioning to PQC to accommodate PQC. So the change is already happening. The candidates are finalized. The change is happening. The final announcement will not be very different from the one announced. So it's very much happening, madam. Now, the next question, if I'm chat window, okay. I'm not able to. Okay, there's a latency, so I'll wait. Yeah. How you control the number of photons? I I can only lose photons. I cannot control. I wish I could control. I could try to do a better alignment, and I could try to use good source, good specifications to get maximum what I can get. So, when millions of photons strike a nonlinear crystal, a birefringent crystal, where it is dependent along with the wavelength, it depends on the polarization. The refractive index also depends upon the polarization, and then you kind of you orient the entire system in a manner that you satisfy the phase matching condition and generate correlated photons, which comes out with some angle in between them. Again, because we have ordered the crystal in that manner, it is called nonlinear, um, uh, non collinear and non-collinear SPDC. And then we orient our collection optics in a manner that I'm able to collect those photons. So it is a lot of hard work. What detector? Silicon detectors. It depends upon the wavelength of light. How can we be sure resistant against the quantum computers? We cannot be sure because the PQC algorithms to be um, uh, are believed to be secure against a quantum computer. I would recommend that we discuss the computational complexity from a quantum computer perspective. See, because if a quantum computer is not able to solve that problem statement in polynomial time, then that particular problem statement can be uh, you know can be developed to be a quantum resistant algorithm for PQC. So it is a good opportunity to also explore them, but it is a hardcore mathematics, with the idea, with the yeah.
Ma'am, two early questions. Is there a stable crystal available instead of a BBO crystal?
Yeah, there are crystals available, and some advanced crystal. I can. I'm still working on, so I will not be able to say different ranges of nonlinear crystals. But at the same time, people are exploring, planar light circuitry. They are exploring quantum dots. They are exploring different ways to generate single photons, higher number, and stable output.
Uh, there is one more question. Does beam splitter also uh, pro- split probability too?
Yeah. So if you have 1 cross 3, then the ket 0 state will become, you will be having a superposition state after the beam splitter in 3 particular paths. 1 cross 2 will have in 2 paths. One path we say ket 0, other path we say ket 1. So it's a binary one. Similar way, it splits the probability into the
Yes.
number of paths.
Yes, ma'am. One institute wants to contact regarding setting up an optoelectronics and laser lab. Maybe I will share the email ID with them. They'll
Sure,
interact.
sir. Yeah.
Yeah. Next one is what detector we use to detect single photon?
Silicon based detectors. So there
Silicon.
is quite a monogamy of of the vendor. I don't want to take their names, but yeah, I mean, silicon based detectors, they give maximum efficiency at an region between 800 nanometers to 850 or 840 nanometers, or 780 to 840, in particular that range. And the if I'm using, usually people use 405 nanometer wavelength as the base, and then if you have a down conversion, means frequency is halved and wavelength is double, so you have 810 nanometer. So it captures that with a higher efficiency. It works in the principle of Giger mode. That means, and so there is an avalanche effect after every detection. So we need to be careful uh, about exposing it to bright light, or even a torch light, or even a laptop if open. It also adds to the count. So it is very sensitive. It is very sensitive. Yeah. Any more questions? Are PQC algorithms developed or under development?
The
I think
question
I've answered.
the question after that, yes. What is the difference between the experiments you perform and the modern quantum computers? I mean, error and many fundamental differences. SPAD.
See, the quantum computer which I have presented here is for education. I would not say it is scalable, because it is all based on the bulk optics. Okay, it is good to explore fundamental phenomena, and then some core application. But if you would want to go for a modern, in the sense a scalable quantum computer, then there are different ways to realize a qubit. Artificial atom, like superconducting one being one of them, neutral atom, ion trap technology. Even in photonics, you can use different degrees of freedom. It can be orbital angular momentum, or it can be a higher dimension where you are doing intra qubit superposition, interqubit entanglement. So it is actually, people have explored many, and you can still look into different aspects. There can be still some different method, a new method to realize a qubit, and that can be scalable, and that can happen in at room temperatures as well. So, but the idea here was, if you know how a quantum computer works, maybe a one qubit, then there is a lot of study which for understanding the noise and how to do noise mitigation. Okay, now a noise mitigation or noise, the cause of noise for different quantum computers from different realization of qubit will be different, but the approach will be the same. So, and even the software stack, from manipulating the qubit in the hardware to executing the algorithm, they are going to be the same. So lot can be mimicked, and it is approachable to academia, to for education purposes. Otherwise, if you would want to work on a scalable quantum computer, I think then then there are companies, there are industry startups who are dedicatedly working on development of quantum computers, and that path can be taken.
Yeah. Last, maybe the concept of terrestrial or free space QAD, it may not be possible to reach out to all the users and associated losses. It may be essential to have satellite-based quantum communication or QKD. Please share your thoughts.
Yeah, so then I think I would like to answer this with one slide which I have, and it will eventually come in the presentation.
Yeah, you can continue with
Yeah.
your.
Okay, thank you. And I'm really humbled by the numbers. So, Pillai sir, congratulations. You're doing a fantastic job. Yeah, and I thank everyone for their interest, because it really takes a lot in, taking out time and trying to learn something different. So thank you for that. And I hope I'm not boring anyone with something which is so counterintuitive and very much, in lower TRL levels. Sir, I'm not able to hear you.
Yeah, the number has been consistent since the beginning. So though they have attended maybe the talk, they still want to reinforce it kind of. I am also following the lecture. So that's where I
Okay.
can see. So I think
Okay.
you are on track. Yeah, thank you.
Okay. Thank you. So now I'll start talking about the preambles of quantum communication or quantum cryptography. It starts with no cloning theorem. So again, if you look into the maths of it, the math says that it is impossible to clone an arbitrary quantum machine. But for curiosity, we start with a possibility. What if there is um, a quantum Xerox machine that can clone an arbitrary quantum state, say just like putting a PDF with a ket 0 as a blank A4 sheet and then trying to get two PDFs? Hmm? So is it possible? Well, the maths says no. But if it were possible, then I definitely know that there cannot be two different Xerox machines for different PDFs. There has to be one Xerox machine for any PDF, right? So let there be ket xi and ket phi as two different PDFs, and we have the same quantum machine. Then the result is ket psi xi, ket phi phi, right? Now, if you take the inner product, and if you do the maths, you will find that it happens only in specific cases. Okay, so it is either the state, one particular state, or its orthogonal state. For example, ket 0 and ket 1. But if you take an arbitrary quantum state, you will not be able to duplicate. So the maths is very clear. You cannot, Eve cannot duplicate the state sent by Alice for future use in a very broad manner. So, so this tells us that, and this is again a page from the book from Elements of Quantum Computation and Quantum Communication, and it deals very nicely with this topic. So, this theorem is one of the bases of quantum cryptography, that I cannot clone a state. My key is about, I had mentioned earlier that my encryption decryption keys are highly correlated states. If they're highly correlated state, and each state is a binary number, so if so unless until they are measured, they are in quantum state. And if I'm trying to look into the state to find out the state of the system, whether which polarization state it is in, or any state which I'm looking for, it is going to perturb it and it is going to change its state. And a beautiful example I'm going to present maybe after 2 or 3 slides. So here again, it is, Wouters and Zurich were the ones who had, this paper talks about that why a single quantum cannot be cloned. It comes, the basis is this mathematical maths which I have presented here, that forms the basis. But it is a good read. And Stephen Weisner was the first person to come up with conjugate coding, and this is how the technique is use in quantum cryptography, any quantum cryptographic protocol, be it BB84, BBM92, COW, DPS, DPR, RRI, any QKD protocol you take. This is one of the strong reasons, or strong, yeah, it forms this the basis of security in any quantum key distribution protocol. Non-commutativity, why this is so interesting? Because I will be using two bases. Okay, I'll be using two bases. Say, for example, I'll be using rectilinear basis and diagonal basis, and these two bases do not commute with each other. Okay, so if I want to explain this in very simple language, so if I'm having this electron coming out from a gun, and these are the two slits on a metal wall. So P1 is the probability distribution if S2 is closed, and P2 is the probability distribution if S1 is closed. Now, if S1 and S2 are both open, then instead of bell curves, I'm seeing a quantum signature. So this observation, this quantum signature tells us that I am seeing a quantum phenomena. It's not a classical phenomena. And S1 and S2, they both are open. Nobody is observing them. The electron, just like a water wave, is entering into both S1 and S2 in order to interfere it with self. Okay. But now if somebody is trying to monitor whether the electron had come from S1 or S2, it is disturbing the as if the quantum state knows somebody is observing the state, and it collapses to a Bell state. Just like the photons, the entangled states in two galaxies, they somehow come to know that what is the state of this, the state after measurement, HH or VV, and it collapses to the state accordingly, satisfying the correlation. Similarly, here also somehow it comes to know that somebody is trying to observe the other particle, and it loses its quantum signature. It becomes a classical signature. So quantum cryptography is all about it. Okay. So here again, it's very important to understand this particular diagram. It tells you the uh, core elements, or core elements of any QKD, which you will come to which will deal here. So they are connected by a classical channel and a quantum channel. A quantum channel can be an atmospheric free space, or it can be a fiber-based QKD. Okay. Quantum states mean the single photons which I have generated, or any quantum particle which I have generated, primarily photons, because photons are like light, they can travel from one place to the other. They will be using this medium, okay, either through fiber or through free space. Now, when the quantum channel or the optical channel is there between Alice and Bob, then Alice and Bob also needs to do some verbal communication, which has information about the key, but will not disclose the key, because key is only formed after this discussions which is happening, right? Which means that it is having some footprints of the key, but it is not having the key. Okay, it is very important to understand that the key is not transferred from Alice to Bob or Bob to Alice. The key is generated at Alice and Bob spontaneously and in a symmetric fashion. Why symmetric? Because it is going to use the quantum correlations. Okay, so after this quantum data transfer, or QKD protocol, we arrive at symmetric encryption keys at both the ends, which is then used for encryption and decryption. And finally, the message is encrypted, and finally, it is decrypted at the Bob side. Okay. So this is the essence. And again, another very important thing I want to tell you is Alice and Bob uses secure classical channel and insecure quantum channel. And Alice and Bob, they only are in the business of generation of keys, not in the business of authentication. So I am using a prior authenticated, a secure classical channel. Any adversary can always listen to what classical channel is, um, they're talking about. So when we are investigating a QKD protocol, we allow that. We do not change anything in the classical channel because we assume that any algorithm which has its basis in information theoretic security has been incorporated. Okay. So if Alice and Bob are talking, then I would prefer to encode them, because if I'm encoding them, then a lesser leakage is there. If lesser leakage is there, then my secret key length will be longer. If I openly talk over a phone, or I broadcast whatever I'm doing, then higher leakage. That means the secure key will shrink more. These are the nuances or things which people do not discuss, and I also face a lot of challenge while propagating this. When I'm making a working prototype, then people do ask me that why are you encrypting the classical channel? But if you study the information theory, the quantum information theory, if you study the security of a QKD, you will know that your information leakage is that we quantify the leakage by quantum mechanics, quantum information theory, and then we shrink the key. We try to reduce the information leakage, and hence you can use any encryption algorithm. I will be using PQC. If you're making a state of art device.
Participant, just be on hold. Ma'am will be joining. Yes, actually, ma'am disconnected. She'll be joining shortly. Just give a minute time.
Hello.
Yes, ma'am. You can continue, ma'am.
Yeah.
Yeah,
So I was
you're
talking
audible.
about I was talking about the Alice and Bob pair. So this is a secure secure channel, and quantum channel is insecure channel, because we are allowing the quantum eavesdropper to apply any information, any measurement to obtain information, and then we are trying to deduce what is the, so we are already categorizing the possibilities. In the classical world, we do not know what kind of technique may come, or if somebody is able to is eavesdropping or not, if somebody is fiber tapping, then we arrive at that information after people have been able to use it, okay, apply those hacks. But in quantum cryptography, we beforehand we categorize the possible attacks, all possible attacks which the quantum physics allows. Then we categorize them into three parts: incoherent, coherent, and generalized attacks. And then we see how much of the information can be leaked as per each category, and then we apply something called as shrinking factor. So now I will discuss this once again in the later slide. Okay, so now the QKD protocols can be divided into two parts. One is based on the nature of QKD, and the other is detection based. So in QKD, prepare and measure, we have two nodes, the quantum transmitter and quantum receiver. The quantum transmitter generates the state, it encodes the state, it converts into a quantum level, or depending upon the nature or implementation techniques, and then it sends it to the Bob. Alice and Bob can be at a distance of about, say, around 90 or less than 100 kilometer if it is line of sight. If it is terrestrial also, it doesn't usually go beyond, unless there is a breakthrough QKD technique like twin field, which stretches it to a greater distance of about, say, more than 150 kilometer. Even in classical, you have classical repeaters after every 90 to 100 kilometer, right? But we cannot have a quantum repeater for a single photon state, because a repeater would be doing measurement and then amplifying it, and we cannot do any measurement on the quantum state, so we do not have quantum repeaters. Yes, if it is an entangled state, then using entanglement swapping techniques and some special techniques, quantum repeaters for entangled photons is theoretically possible, and people are working on working prototypes, and hopefully that should come to market in very near future. In near future it will come. The other one is the entanglement based. So you have got flavors of both in this presentation. So in entanglement based, I had shown you there is a Charlie which generates and transmits, and it's a two particle. So there are two receivers, and a quantum communication happens between the two receivers. The transmitter only generates and sends the state. He is a trusted person who will generate the entangled states. But at the same time, since you are doing entanglement based measurement, even if it comes from a person whom you do not want to trust with, it is still okay as long as it violates the inequality. So such is the power of measurement device independent cryptography. Now detection based, because it is again it depends upon the nature of photonics you are using, if it is discrete, a single photon states, or it is a continuous variable. But in this particular presentation, we will not worry about the discrete variable or continuous variable. We will study more on the prepare and measure and entanglement based QKD. So to begin with, let us start with few polarization states: 0, 45, 90, and 135. 0 and 90 degree, 0 degree, 90 degree, they are 90 degree apart. 45 degree and 135 degree, they are also 90 degree apart. 0 degree and 90 degree polarization, they form one basis, which is the rectilinear basis. And 45 degree and 135 degree, it forms another basis, which is the diagonal basis. So now the question is, how will I be able to identify the states if 4 of them has been sent? And if I ask a question, say if if I'm asking a question, means I am actually using some kind of a measurement device on the input state to infer the state of the system. If it is horizontal or vertical. So what I'm saying right now, maybe anybody from physics background would be able to understand. There is a polarization beam splitter, polarizing beam splitter. If you have a horizontal, it will get transmitted. If you have a vertical, then it will get reflected. Okay. So if I'm using a polarization beam splitter in front of a single photon, which is horizontally polarized, it will pass through. So if I get a detection here, I know that it is a horizontally polarized light, or the photon was horizontally polarized. If I get a measurement here, then I know that it is a vertically polarized photon. Okay, so if I know that the photon is either horizontal or vertical, I will be using some optics, a special optics. Similarly, if I know that my input state is 45 degree or 135 degree, I will be using a measurement device that can differentiate between these two states clearly. Okay, so some special optics along with the PBS I'll be using to differentiate, such that if I'm getting a 45 degree, then one detector click corresponds to that particular state. And if I'm using 135 degree light polarized photon, then another detector, a separate detector, it clicks, which tells me that it is a 135 degree polarized state. Okay. So now let us see this mathematically. So some maths for you. So why I'm able to clearly differentiate between two rectilinear bases, why I'm able to differentiate between two diagonal bases, why I am not able to differentiate between a rectilinear basis and diagonal basis is given in these three equations, in these six equations, 1, 2, 3, 4, 5, 6. You can see the m plus and m minus, these are the measurement operators from diagonal state, from and a horizontally polarized state. And if you look at this particular state, m0 and m1, so m0 and m1, then they commute, which means I can measure them with certainty. The diagonal measurement operators from diagonal state, they commute, I can measure them with certainty. But measurement operators from rectilinear and diagonal base do not commute, and therefore I cannot measure them with certainty. So this is a complete maths, or the secret why such thing happens. Now for students, you can explain this in this manner. You can have a classical box. So you take a classical box, and so if you're looking into the screen, you can look into what I'm trying to represent it here. If you have a classical box and you have a ball inside the classical box, and there are two doors. Okay, there will be four doors. Let me take two doors. If I'm opening the box from my from the front, whatever the color of the ball is, if it is a red ball, in the classical box, whichever side I open, it will always be red. If I'm opening front, if I'm opening diagonal, I will always see the red color. If I keep doing it for the rest of my life, every time I open, I will see the red ball inside it, because I had put red ball inside it. But if I'm putting the ball in a quantum box, okay, and I'm putting a quantum ball inside a quantum box, okay, so if I know I have put a horizontal or a vertical polarized state inside it, okay, and so before that, please look into this box, and you will see M01. M01 corresponds to rectilinear measurement, which means the PBS, the polarization beam splitter, when the state was 0, red or gray, or 0 or 1. This is the diagonal. This side is equivalent to doing a measurement in the diagonal basis. So plus and minus stands for plus 45 degree and 135 degree. Okay. So if I'm having a red ball, please listen to me very carefully. If I'm having a red ball inside the quantum box and I'm opening the M01, I will see a red ball. I open it several times, I will see red ball only, because I'm using the right measurement operator, and also because I know the state. But similarly, if I'm having blue or a green, I will tell the person who is handling the quantum box, please open diagonal side only, because my state is diagonal, blue or green. So whenever my diagonal side opens, I will always see the right. If I have sent blue, I will see blue. If I have sent green, I will see green. Now the beauty of quantum physics lies if I do not know the state. Okay, and that is the basis of BB84 or quantum cryptography. If I'm putting a red box inside a quantum box, and say the communication link between me and the person holding the quantum box, there is a glitch and he cannot hear me. So he randomly opens the incorrect side of the box to look into the state, okay, which is plus minus. So plus minus, my friends, corresponds to green and blue. Okay, so the person is going to see either a green ball or a blue ball. Okay, so a horizontally polarized state will become either a green ball or a blue ball upon incorrect measurement. It has disturbed the state of the system. He will never see blue ball or green ball all the time. It will be randomly collapsing to either blue or green. The randomness is there again in the maths. Okay. Similarly, had it been had I sent a blue ball and I would have opened the rectilinear basis side, I would have seen either a red or a gray randomly. Okay. Had it been the correct side, I would have seen the correct state. Okay. So quantum cryptography is as simple as asking the right question and then disturbing the link between the person who is doing the measurement and the person who knows what the state is. Okay. So here, this slide is the easiest slide, where Alice and Bob, they have a link, and then Alice and Bob is actually telling Bob which one to open. If it is a red state, it will be question 1, the rectilinear PBS. And if it is a diagonal state, then Bob will be opening the other side of the door, or the optics with PBS. Okay, and you will get the right state. So right question, right measurement. But what happens if the link between Alice and Bob, particularly uh, particularly this kind of a communication where Alice is not supposed to send the state of the system to Bob. Okay, so what happens then? In case of incorrect, now randomly Bob will open the right one, and randomly there will be cases where he will do wrong measurements. So when he's doing wrong measurements, as you can see here, he is disturbing the state of the system. Red becomes green and blue, blue becomes red and gray. Okay, so you are getting random answers. So this is the fact. So right question, right measurement, you will see the right state. Wrong question, you will get random answer. Wrong question damages the state, original state. Only Alice knows the correct question. Eve will guess the question and will introduce disturbance. So the last sentence is very critical, and that is why we say that Eve's that I will be able to detect any tampering or any monitoring of the state in case of quantum communication. So now the question of I will answer that question in through the slide. So to achieve an all-time, all-location quantum communication, I need to establish a link between all modes of quantum communication, all modes of communication, whether it be satellite, whether it be aerial, and whether it be terrestrial. So a connection between all these three modes is essential for achieving a quantum internet or quantum communication network all around the globe. So a lot of national efforts are there towards terrestrial QKD network, and ISRO and they're also working towards satellite QKD. And what we bring is the aerial QKD network. Okay, so the aerial QKD network establishes a link either between a satellite and a terrestrial. At the same time, it caters to agile and ad hoc requirement for key distribution. Agile, it is based on a condition. If suppose there is a war condition or there is some a necessity to fulfill some part of the link, it will go and establish itself. It will deliver the keys as on the demand. So the QKD architecture comprises of I'm going a little bit in depth about a QKD architecture. It will have the following, layers. A QKD protocol will be something associated with data transfer using that quantum link. Then we have sifting, we have error estimation and error correction. Now, there is a lot of analysis which happens in order to find out the data leakage. Then there is another layer called privacy amplification, which tries to decrease the mutual information between the adversary and the Alice or the Bob. And finally, we generate the secret keys at either ends. Now, when we start off, we have millions of data, but when we end, we have secure symmetric keys, which is about 1/3 of the size of what was actually received, because lot of filtering happens because of the electronics, because of the time, because of the optics, okay, and the different processes involved. In error correction, we share a part of the bit, part of the string to Alice, in order to estimate the key error rate, okay, and if it is exceeding, then we drop it off, then we again start. So a lot of analysis happens here. So this is the complete architecture of a QKD system. Now, as I had told you earlier, there are two types. The quantum channel can be fiber or free space. So the data transfer can happen either in free space, for example, between two towers, or it can be between two buildings over a dark fiber. And the source can be entanglement based, or it can be weak coherent source based, or it can be single photon based. These three can be implemented via optics or via some other technologies which has a higher generation rate. The classical leakages can be estimated based on some standard prescribed techniques. Now, there is no standard QKD protocol, but a BB84 protocol with single photon source is one of the robust QKD protocols, and which can actually survive even an adversary having a quantum computer and a quantum memory. Okay, so it is most likely will be one of these candidates for standardized QKD protocols. Security requirements. Now, security requirements here particularly points out to the quantum channel. As I had mentioned earlier, that the quantum channel is insecure. So whatever security patches while security evaluation, if there is a chance of leaving footprint through some other degrees of freedom, that is taken care of. So the QKD architecture is again a layer, because once you have generated the keys, you need to store it, you need to archive it properly. It has to be, it has to be maintained, and it has to meet the highest security standards, and all that is a different engineering area altogether. So I would say that, exposure of again quantum technology devices to education, to the quantum education, rather than a QKD device, buying a QKD device, it makes more sense, because the students builds understanding of the subject and will be able to cater to different applications within quantum communication, and not just a particular QKD protocol of which maybe they be referred. So I would strongly recommend that to for any academic or any R&D center of excellence, such education modules which allows a broader education on the quantum principles and is not specific to a particular application brings more value to the ecosystem. I think I will keep the other slides for some time, because they are mostly on quantum communication. And as Pillai sir has already now announced that, I will be taking uh, those lectures, so I will keep it for that time. And those will be primarily on entanglement-based QKD and prepare and measure QKD. I will be showing you the lab output. We have already demonstrated entanglement based and prepare and measure based QKD protocols in lab. So we will share those results to help you understand how the communication protocols lead to development of these binary keys, so from analog to digital. Yeah. Sifted key actually is a process. So if I'm using two different bases set, for example, in BB84, that makes sense. Otherwise, if I'm using two I would say non-orthogonal states, two non-orthogonal states like in cow protocol or in DPS, their sifting is parameter is 1, so we can leave that. So sifted key, madam, the exact process till the key generation error estimation. Yeah. So what is the question? What if we get to know Eve's presence? So we will get to know Eve's presence while we are doing the error, estimating the key rate, error rate. So because I know if there is an eavesdropper in the system, they are going to leaves the footprint in by having a large, significantly large, significant error rate. For example, you can look into the man in the middle attack for B92 or BB84. So there, the error rate doubles. The maximum threshold error rate for BB84 after an eavesdropper has attacked or man in the middle, it doubles, right? So that actually gives you an idea. In fact, we closely monitor the system parameters to understand whether the eavesdropper is acting smart, because he can actually exploit any loopholes of implementation. And there will be certain attacks where footprint is not left. So we have to carefully um, understand what are those possible errors and understand the leakage involved. Then we take care of it during the privacy amplification. So what if we get to know if such a, do we give up that? Yes, we give up that. We do not incorporate that keys at all. We stop the cycle. If not, how can we be sure? Yeah. Any more questions, sir? I think. Durgesh ji, what if Alice and Bob's photon are entangled with one of the eaves? Okay, so when you are generating the state, so the quantum attack happens after the photons leave the transmitter. Now, there are some research on possible loopholes if the security perimeter is not defined properly. For example, if somebody is monitoring the Alice's generator, okay, but that again doesn't lead to creating an entangled state within Alice's transmitter. So they can always use a quantum probe and attach the probe with the Alice's photons, and that is how most of the attacks, incoherent attack, and that takes place. So entanglement may not be there, but they will be attaching the probe. If that leads to an entanglement, that has to be seen. Because as I told you, entanglement is in the generation, so it will evolve. The state is going to get evolved. But that's a very good question.
Do
Does the
sub-Planck,
Yes,
you
sir.
can, yeah. Do sub-Planck structures have any role in quantum cryptography? Earlier question.
Would state collapse if Eve do Eve's? No, sir, I'm not able to see that question.
That is at 429, 1629.
1629.
Earlier.
Okay.
You can answer the last and then go back. Yeah, either way.
Okay, Madam, do sub-Planck structures have any role in quantum
Quantum.
cryptography? I may not be able to answer that with certainty. Maybe, we have to explore that. I don't have a straightforward answer for this question. Is at the output of P12 normal distribution? So here I would mean to look into the quantum interference effect, because the electron is entering both the slits,
Okay,
uh,
also okay.
So from that perspective, it is a quantum interference and not a uh, normal distribution. Problem. Sifted key, I have responded. If Alice and Bob's photons are entangled, okay. What state would collapse if do eavesdropping entangled states? So in entangled state, I've already mentioned it's HH plus VV by square root of 2. If the state collapses, it will be either HH or it will be VV. Okay. So and here again I'm considering there is no noise, because if you have noise in the system when you're measuring the output, it's very difficult to understand whether the HH is from maybe one detector count or one false count or not. So those have to be calibrated, and the system has to be engineered very well. But in case of an ideal condition, it will collapse either to an HH or to a VV state. What if we get to know Eve's presence? Do we give up? We know, if we know Eve is eavesdropping, then we immediately discard their process and we again start new. Yeah, I think. How can we be sure that Eve's presence will not contribute in the next instant? Yeah, that's a good question. Um, So that is, it's very difficult to answer, because once I know that the error rate is high, it is either somebody is perturbing the channel, most likely it is with the current capabilities, it is mostly a man in the middle attack. So we will try to use an alternate channel. What happens if, so this will be a case of denial of service. So either I will be using, and when you're using it for a particular application, any disrupt if the channel gets disrupted, then you'll have to go for alternate measures. So it is advised that we go for the alternate methods and keep encrypting, at the same time trying to understand where first of all we make sure that it is not because of some ambient factors, or trying to, so it has to be again calibrated. Particularly if after calibration also I'm able to see high error rate, that means somebody is monitoring. So we take the alternate and next path, something like that.
Yeah. Thank you so much, ma'am, for your valuable time, and all the queries have been answered. And yeah, participants, hopefully you have had a peek into some of the things, and especially as clinicians, what we can do is there. So there is a little bit of investment and all that we need to do, and then these experiments can be shown to excite the students, and we can try to take these things forward, and students will understand some of the concepts which are more in the abstract sense we are explaining, but we are able to try to show them and demonstrate. So that will actually help us to say that, okay, this is how a quantum computer is going to look like, or how it's going to be created. So that's like explaining the building blocks. So that's where this session is placed. So hopefully you have understood, and maybe Department of Physics, Department of Electronics can come together, Department of Computer Science, you can set up these labs together for the benefit of the institution. So hopefully you will take it forward, and then you can contact ma'am also, and for any further this thing that you would like to seek an advice to set up a lab or something, So that's where ma'am has guided us also. In MNIT Jaipur, we have tried to take the advice, and then we are trying to set up the lab as per whatever some of those things are there. I would suggest anybody to connect over LinkedIn. So you can just look up, most of our resource persons are on LinkedIn, and they will appreciate you to contact them, and they will respond. Most of them respond very quickly, and at least in a day's time, you will get a response. So you can take it forward, right? And then, of course, you can connect with me. I can connect it to the resource persons, and I will share the email if required. So the best way is to go through the LinkedIn profile, and that's where we can connect. That's the easiest way. And thank you so much, ma'am, for being with us. Thank you for sparing your valuable time. Participants, tomorrow we'll meet again at 3 o'clock. But today will be the last option to take quiz 2. So we will close quiz 2 at 12 o'clock today, 12 midnight. Quiz 3 is open till tomorrow, and quiz 3 will close after that. So please try to understand that you have to complete quiz 3 by tomorrow. We want to release the certificates this time on Monday. 29th Saturday, we close the course, and Monday we'll try to give the certificates. So please complete your quiz 3 tomorrow, and there'll be no more further extensions. Please try to cooperate with us, and we will also consider some of you, if you have completed 0, 1, 2, and 3, and other 4, 5, 6 courses of the other series, then you can be admitted into the offline program that will be conducted. So we'll try to share the details. A lot of constraints on us as of now. Immediately, we are not able to tell. Our college schedule is also very tight. There are some interviews going on here, and there are some issues that we are not able to finalize things. So we'll come up with the schedule shortly, and hopefully you will have that. We'll try to make it more easy for you. That's what I can say. And hopefully we will also look at how to go about, right? So thank you so much for all these things, and we'll meet tomorrow. Tomorrow and day after, Dr. Ashwath Babu will be taking the session. So please be ready. Please complete the quizzes, and we'll meet tomorrow at 3 o'clock. Thank you so much.